Well, we're going to work on some notes today for extra topics that Vincennes requires. And these are, first of all, bases other than E, where we take the derivative of those. And so we'll look not only at an exponential, but also at a logarithm, where the base is something other than E. So you have um, basically two new rules. The first one is doing the derivative where you have a base of a to a variable power. And so you'll notice that that derivative is the natural log of the base times the base to the power itself. And the alternative on that is if the exponent is something other than an x, then you need to multiply by the derivative of the exponent using the chain rule. For logarithms, where the base is something other than an e, then we will do 1 over the natural log of the base times 1 over x. And both of those then will end up being in the denominator. And then likewise, if the argument is something other than just an x, then we'll need to do the derivative of that argument. I've got your three properties of logarithms that you may have to use along the way, and a reminder that all other derivative rules still apply, like product and quotient and chain rule. So we're going to look at two examples to get started. The first one is where we have a base of 3 with a power of 2x. So doing the derivative with respect to x of 3 to the 2x, we'll first of all do the natural log of the base. So natural log of 3 times the exponential 3 to the 2x times the derivative of the exponent 2x, and so the derivative is 2. And then just to simplify that a little bit, just rearranging things, we could put the 2 in front of the natural log of 3 and then times 3 to the 2x. You might also see that written as 9 to the x power because you could go ahead and square the 3. All right, then your second problem is x times 6 to the negative 2x. And I tried to emphasize times because you're going to need to do the product rule. So we will start this off doing first times the derivative of the second. So like our last one, the derivative of 6 to the negative 2x is the natural log of 6 times the exponential itself, 6 to the negative 2x, times the derivative of the exponent negative 2. And then we'll do plus second, which is 6 to the negative 2x, times the derivative of the first. And the derivative of x is 1. So there's the calculus line. And then the simplification for that, we have 6 to the negative 2x as a common factor. We can take that out. And then rearranging just a little bit, we'd have negative 2x times the natural log of 6 plus 1. And those are your first two examples. All right, for this video, we will be concentrating on the derivatives of logarithms when the base is something other than an e. So this is a reminder that your rule for this is we'll do 1 over the natural log of the base times 1 over the argument. And then if the argument is something other than just x, then we have to multiply by the derivative of that argument. So I'm going to be looking at what I have labeled as examples 3 and 4. For example 3, we've got y equals the log base 3 of x squared minus 3x. So our derivative, y prime, will equal 1 over the natural log of the base, and we'll multiply that by 1 over the argument, x squared minus 3x. And so I'm just going to go ahead and write that all in the same denominator. Because the argument is not just an x, we have to multiply by the derivative of the argument, 2x minus 3. And then we'll just make that look nicer by putting the 2x minus 3 in the numerator and then rewriting that denominator. So you would have the natural log of 3 multiplied by x squared minus 3x in the denominator. So there's the first one. Now the second one, number 4, we have y equals the log of x squared minus 1 over x. And so you may think we need to do the quotient rule, which could be done, but I would rather that you think to rewrite this. So remember, your properties of exponents would say that we could rewrite this as y equals the log of x squared minus 1 minus the log of x. And then we'll do the derivative. So y prime would equal 1 over. Now, this base, when it is not written, is understood to be base 10. So this would be 1 over, I already wrote the 1 over, excuse me, the natural log of 10, and then multiplied by the argument, x squared minus 1 in the denominator, and then times the derivative of x squared minus 1, which is 2x. Minus, now we'll do the log base 10 of x. So that would be 1 over the natural log of 10 times 1 over x. So we'll put the x in that denominator. And then just to be consistent, we'll multiply by the derivative of the x, which is a 1. So we can simplify this a little bit, writing the 2x in your numerator for that first fraction. And then in our second fraction, I'll just leave that as 1. Let me fix my writing. So minus 1 over natural log of 10 times x. Another bit of simplification is we could factor out 1 over the natural log of 10 and then have 2x over x squared minus 1 minus 1 over x. And we could work to get common denominators for that. All right, I have one last example that I'd like to show you, somewhat of an application of this type of derivative. So if we have the problem y equals 5 to the x minus 2 power, we could find the equation of the tangent line to that function at the point 2, 1. And so to do that, we would first of all need to find the slope, and we find the slope by finding the derivative. So your derivative, y prime, would equal, so we do the natural log of the base, and we multiply that by the exponential, 5 to the x minus 2. And then we multiply by the derivative of the exponent, which is 1. So at the ordered pair 2, 1, we would substitute in. So your slope, which is y prime, would equal the natural log of 5 times 5 to the, now we'll plug in the x, which is a 2. So 2 minus 2 power times 1. Well, that would be 5 to the 0 power right here, which is 1. And so your slope would end up simplifying to just the natural log of 5. And then to find the equation of the tangent line, of course, we could do y equals mx plus b and substitute in 1 for the y, the natural log of 5 for the slope. X is 2, and we would solve for b. So b ends up being 1 minus 2 times the natural log of 5. And then substituting that into your equation, what we would be finally giving as an answer, y equals your slope, natural log of 5, x plus what we found for b, 1 minus 2, natural log 5. And again, that's the tangent line equation. So those are your examples for your problems involving bases other than E. And this is going to be homework 65.